Okay, so this is video number 1 of chapter 3's example number 1, which is hydrologic modeling. And so in this video example, we're going to do the first step, which is to, of course, get a digital elevation model. We'll download a DEM, in this case from Open Topography. And we need to make sure that our DEM is seamless, and Open Topography will do that. But if you download your DEM from, say, another source that uses tiles, and you need your watershed to include multiple tiles, then the first step would be to mosaic those tiles together into a new digital elevation model, or to mosaic them to a linked file. But regardless, you need them to be a continuous DEM. So that's the first step. So here we are on Open Topography. This is a great website for all things topographic in GIS. And so a good place to start is to either sign in or just go to find a data map. In this case, we're not going to use actually high resolution topography. We'll just use regional scale DEM. So I'm going to skip signing in. But a lot of times you need to have your sign in to download certain high resolution data sets, especially those associated with the 3D elevation program, the 3DEP program. And so make sure early on that you have an Open Topography login that sources a .edu website, which will enable you to have access to 3DEP data. Okay, so here we go. In this video example, I'm going to be doing a watershed for the Spanish Fork River, which comes out of this canyon right here and includes this Diamond Fork River over here. So I'm going to get a pretty big area. So I'm going to select that whole area, try to get the whole watershed. And yeah, so I'm going to skip it. So after I've selected that area, it gives me options, and these are all the high resolution data sets that are available, but I just want a global DEM in this case. And I'm going to choose this 30-meter ALOS World DEM. And so, yeah, here's that data area. It's 11,000 square kilometers, and I want to download it. So I just give them my information. I don't really want to sign in. I just want to submit. And when you use Open Topography, you can just sit there and wait, or you can leave that website. It'll send you an email with a link to where to download that data from. Okay, so while that's happening, it's pretty quick. I guess we can just save that to my folder. Chapter 3 example, save. Okay, so then, all DEMs and other GIS data typically comes as a zip file. So we need to make that accessible. So in my folder, you can see it's downloaded here to this rasters AW3D30. So that's ALOS World 3D elevation 30 meter. It's not really 30 meter. It's a kind of like 1 arc second, which is about 30 meters, but we'll see what it is in our area. So in Open Topography, we go get a zip file. I can see it says .tar.gz, so it's probably got multiple zips. So I'm going to extract here, see what comes out. And you can see it's still a zip file. So now it's just .tar. So I right-click, extract here again. And there it is right there. Okay, so if you're confident at this point, you can delete those zip files because that's what you need. Okay. So here is my project. Now I'm going to just drag that file in here. One way to get the data in. Hope. There. So I've got it set up to build pyramids right away. Oh, it did come twice, of course. So here's the Spanish Fork River. There's Diamond Fork. And you can see that kind of the ridge line back here of Diamond Fork goes through here. Here's the main Spanish Fork, kind of ridge line comes up. There's probably a drainage divide up here somewhere. So I think I got everything I need, so that's good news. And you can probably see that it's looking a little squished, the state of Utah. That's because these are in geographic coordinate systems. And so, when we're doing hydrologic modeling, a lot of what we're doing is similar to like trigonometrical calculations that you might do with other tools in Spatial Analyst Toolbox in GIS. So it's a good idea to probably transform this into a Cartesian coordinate system. And, so the basic things to set up our hydrologic modeling is we need a DEM. We've got that. The DEM needs to be seamlessly covering our whole watershed. I think that's the case. But again, if this was tiles, then we'd have to link them together or merge them together. That's done though. Then we need to go to analysis now, and we're gonna convert this to another coordinate system. So we're gonna go to toolboxes, and we will, I believe, go to data management and raster data set. No, it's not right. Probably in there, not the correct one here. So let's see. I'm going to do project raster. Okay, so that is in data management tools, projections and transformations, and then project raster. So our raster is this one. We want the output coordinate system to become a Cartesian coordinate system. So I'm going to go to projected, UTM, North America, NAD 83, 2011, 12 North. Okay. So it was in World Geographic. We're going to change it to NAD 83, 2011. Nearest neighbor is going to be fastest, but if you want probably the best result, I'm going to use something higher level. We can see some information on that. So nearest neighbor will be used, minimizes the change to pixel values since no new values are created, fastest resampling technique, suitable for discrete data such as land cover. So it's not the best for what we're doing. Bilinear calculates the value for each pixel by averaging. Suitable for continuous data. We are using continuous data. Cubic convolution will be used, calculates the value of each pixel by fitting a smooth curve based on the surrounding 16 pixels versus the smoothest image, but can create values outside the range of found in the source data, suitable for continuous data. So it could introduce some smoothing of the topography. So I'm not sure that I want to do that. So actually, I guess I'll do the bilinear interpolation. And then we can see the output cell size is going to be, so it's not 30 meters, it's 27.2. And you can leave it as that, but if you don't like that, you could change it to like 27 exactly, or 27.2. I don't like all those decimals, so let's just do that, 27.2. Okay, and you can choose a registration point for this. I'm not going to do that right now, but you can specify like where's the corner of this raster, something like that. Okay, so project raster. This is going to create a new raster. Okay, so it's now loaded here. Not much looks very different, but that's because our map is in geographic coordinate system. So let's turn off our old one. And then let's go to properties of, not the raster, sorry, the map. And then we go to coordinate systems, and we want to make it the coordinate system of this one. Okay, so that looks more like I expected it, less smooshed. Okay. So I'm going to remove that. Okay, so here's my projected raster. And then, so we haven't done any hydrology tools yet, but we're about to. So if we go to geoprocessing again, we've projected our raster. Hydrology tools are in the spatial analyst toolbox. So of course you can search for them. They've got their hydrology toolbox here, and there's quite a few things in here. Remember that in these toolbox, everything is just alphabetically ordered. So it's not like the first thing you do is click basin. No. They're just alphabetically listed by their names. The first step when we're doing hydrology analysis is to do a fill. It says here, it fills the sinks in a surface raster to remove small imperfections in the data. So basically, if there's like little holes in the data where it's a little lower than the neighboring pixels, then it's kind of like an internal sink, and that's going to fail if we do this hydrologic interpolation. So this is a necessary step. So the first thing we do is fill the DEM. So I go to that projected raster, and I'm going to output it, and I'm going to call it fill Spanish Fork watershed DEM. Okay, and run. So it's going to go through and basically identify any small kind of divots or holes where there's like a little low area, and it's going to fill them up to like the highest neighboring pixels so that water modeled would run off of the surface and not pool up there. Okay, so there it is. It didn't change things too much, although if you look, you can see the lowest value in the filled DEM is 1368 meters, and the non-filled is 1327. So that does seem to indicate there was some sinks. Okay, so I'm now going to remove the other one. We're just going to be working on this filled DEM. Okay, so this is basically where we're at. So step one, we've prepared the DEM for hydrologic modeling. We have downloaded DEM. We've made sure it covers the watershed area completely. Otherwise, we'd have to run the watershed modeling twice, and that we don't want to do. And then we've projected that DEM into Cartesian coordinates. This is going to be helpful for some of our analyses later on. You can run it in geographic coordinates. It will work. But in some things, like when we're making topographic profile and things, it's not helpful to have mixed units in different axes. So that's why Cartesian coordinates. And then we've filled it. Okay, so that's step one. So I'll end this video and I'll start another one for step two, which is talking about a flow direction raster.